conservation of linear momentum. Got that right there. And there, for two particles in 3 dimensions, we just have the linear momentum 4 is equal to the linear momentum after the collision. And for the after the collision, I just use primes. So that just means after M2V2 prime. So that's conservation of linear momentum. Then we're going to go to this fundamental, interesting case where they collide and stick together. I'm going to show you that in a minute here. Well, so if they collide and stick together, then you account for that by saying the mass is now combined and they're moving together with their common final velocity. And then we investigate the one-dimensional case where V2, the initial V2 is 0. So this is just sending one object to collide with a second one that's at rest, right? And then they move on together. In the third frame here, they're stuck together and they're moving with their common speed. So when you do this one, you have M1, V1 before the collision, M1 plus M2, V prime after the collision. Equal masses, you'll have half the speed after the collision and before. But when you ask about the energy for this particular scenario, what about energy? Question mark. Then you see something interesting, because the energy before, I'll just write here before, energy before the collision was just a half M1 V1 squared. The energy after, which I'll call T prime, is a half sum of the two masses, V prime squared. And this is where it gets interesting, because we have the V prime right up there. So we solve for V prime, square it, and we're going to end up with, when you do a little bit of arithmetic, we're going to end up with, we square this, we're going to end up with one there, an extra M1 up here, and an M1 plus M2 in the denominator. So this is a good way to write it, because you've got the initial kinetic energy times a factor that is less than 1. And could be substantially less than 1. And that was the question of the lost energy. But we cannot answer at this level of abstraction. And what we argued was, in reality, these particles have internal structure. So that was the argument we ended up with last time. So what I'm going to just put in here in our notes, T prime is less than T, and energy is lost in scare quotes. It's lost to this this view of things, but it's not lost to the universe. It actually or some other internal degrees of freedom. So this is the essential point to clarify before one continues with this whole discussion of collisions. So having clarified this, then we can set up some other interesting problems that we'll otherwise make a total, that we would otherwise make mistakes on. Because since we just had point particles colliding, we could have easily assumed energy is conserved. Right? In fact, we see no reason for it not to be conserved. But it is definitely not conserved. So we don't have conservation of energy when we do this type of collision here. And this one where they stick together, it's called the perfectly inelastic collision. When they stick together, perfectly inelastic collision. want to start this topic off in this way, so we can see what's going on here with regards to energy. Anyway, so I brought this demonstration here. I'll let you get started with it. So I brought the so-called frictionless track, and these cars have Velcro on them, so you can get a collision where they stick together. And air track would be a little better, but this also has its advantages. So literally equal masses, this thing sticks together and they move off with half the speed. Of course, then they actually come to a stop because of friction. But so we're looking at this V prime here, right? Let's go ahead and write it out. So the V prime M1 V1 over the sum of the masses. So that was equal masses than we expected and saw roughly half the speed. But suppose I put some bigger mass on this side. In fact, let's see if this thing can handle a full kilogram. Then when we come in here and collide, it just carries it along. You don't see so much slowing down. And in the limit of M1 being much larger than M2, in that limit, you can neglect the M2 and then V prime and V are the same. This is like when the fly hits your windshield. Okay, it doesn't slow your car down. On the other hand, suppose M2 is much greater than M1, and then I come in with this smaller mass, and the barrel moves. And so we're always looking for limiting cases in this subject, and we can even see. So if M1 is much, much larger than M2, we're not going to be slowed down at all. We're just going to continue on through. On the other hand, if M2 is much, much larger than M1, in the limit of this one being, going to infinity, this one comes to a dead stop, right? That's running into a wall. The wall is essentially not budging. So yeah, we have all the limiting cases here, and you can then see the final kinetic energy. If M2 is so large, it's going to be zero. You're just going to slow, it's going to come to a dead stop. If M2 is very, very small, the final kinetic energy and the initial are almost the same. So you have all these limiting cases, and these are pretty sensible. So you see this in football, right? If we were to stand there and some big linebacker runs into us, provided we don't stick the other hands off, but yeah, they're just gonna plow right through us. Okay. So no matter how much heart you have, right, if you don't have the mass, then some things you just can't do. Okay. Now the other, so that's kind of a prototypical situation. The other interesting one, and this is where these cars are actually better than the air track. I better make sure I'm close to the right side of this thing. So these are better than the air track because what we have here is magnets. Right? So this is a no friction collision. You guys know what happens when equal masses collide elastically?
They bounce back the same amount of force.
Do they bounce back or not? So the equal mass is a really interesting case, and we'll calculate it later, but it's good to see. Dead stop, right? Dead stop, and only with the equal mass do you have a dead stop. So, and you can see momentum is conserved, but in this one also energy is conserved, and that'll be a bit of a proof, right? We'll do it. Now, then you have those other cases. So if we do an elastic collision against the larger mass, you'll see it gets complicated. This one bounces back, and this one moves forward. So this is a good one, but again, this equal one is the one to hold in your mind in terms of expectations. It's got this symmetric aspect to the masses, dead stop, keeps going. So we saw if we have a mass here, there's a little bit of bouncing back. What if we come in here with the big mass? This is also a real prototype. A and then slowly, and it launches with more speed. So we're gonna get a calculation for that one as well later on. And then everything in between too, right? Everything in between, we could be putting smaller masses on here, getting those effects. But, the one to look out for is equal masses, elastic. You could say that's a defining characteristic of the elastic collision. It's symmetric in that way. Good. So those are the demos I wanted us to see. And we'll be able to demonstrate all those things mathematically. In fact, what we'll find mathematically is if this mass is much larger than this target, the target is launched with exactly twice the speed of this one here. So we'll get all those things. So next I'll write down for the record, and we had that last time at the end of the hour. We had the inelastic collision. And for the inelastic collision, we have momentum is conserved. And for things in this vein here, energy is not conserved. Not conserved. So this is the one we're going to work on a little more, and then we'll get started on the elastic collisions with their characteristic as well. I know we've seen them both in practice. So I'd say the important application of the inelastic collision, there's a couple, but a really important one is the ballistic pendulum. You guys remember the ballistic pendulum by any chance? Ring a bell? So I'm gonna set that up. This is a way to measure the speed of a bullet safely. But it also, it makes use of the stuff that we're just looking at here. So we'll set up the ballistic pendulum, we'll set up some two-dimensional collisions as well. And then I'll make up some kind of alignment just so we can have a little practice on these. So the example, we actually built something that demonstrates this in the department once. Have you guys seen the air pressure cannon yet? Should bring that in next semester.
I don't.
Ping pong balls and all. They may have had it out at the barbecue before. But,
I don't.
yeah, you know it. You'd remember if you had.
Yeah.
But, so ballistic pendulum. And we'll actually demonstrate, I think we'll demonstrate this sometime next semester. Ballistic pendulum. So the idea is you have a speeding bullet, we'll call it lowercase m and v, and you shoot it into a block of wood. So it's gonna lodge inside the block of wood. Now, if you did this on the track, you could actually just use the calculation we had just done a minute ago. So we're gonna call this capital M, but to turn it into the device we're gonna measure with, we suspend it like this. A couple strings. And of course we have gravity pointing down. So there's weight there. So the first part of this calculation is that we have conservation of momentum. Now when this thing collides here, it is going to kick this thing forward, and because of the nature of a arc, it will initially be moving horizontally, right? The idea is it's gonna move horizontally and then it's gonna swing up. And so eventually it'll swing up to here, say, okay. And then we'll have two masses. And let's see. height difference. And of course, it's gonna swing back right away. But what you do is you just build a pointer here. You build a pointer that gets pushed, and then it swings through a certain angle. That's how ours works. It pushes a pointer up, and then when it swings back again, we've got the pointer with the angle. From that, we can calculate the height, no problem. So that's the idea there. So the height is available. And that's the whole thing, right? You fired a bullet at this thing, it swings up, swings back and forth, but now you've got the final height. So the first thing we have, and I'll call that over here, we have momentum conservation. And same calculation we did a minute ago, we'll have mv equals small plus large mass v prime, instead of 1 and 2. So that'll be our first equation. Now the second now, this is the really important note, we don't have energy conservation in this before-after situation, okay? But, so energy not conserved, that was the big lesson of that inelastic discussion. So not conserved. But after this collision, so after the block and the bullet are now joined, and after they're moving, then we can claim energy conservation. So we have energy conservation for the process when it swings up. So that's why you have to separate these two. So I'll write energy conservation after so that's, this thing is now moving and it's gonna move up the hill, and then we just do the standard 1/2 total mass v prime squared is equal to total mass gh. You guys are used to doing this, right? What we did was we took the kinetic energy, set it equal to the final potential energy. That's when it's there up the hill. Okay, so the separation of those two processes is key. And yeah, so then what are we looking for? We're looking for the speed of the bullet. That was our goal. We could be looking for other things. So we'll go ahead and solve for the initial v and just see what happens. So now v is equal to the sum of the two masses divided by the mass times the v prime. And we'll just plug in and see what happens. M over M. And that v prime, here we're canceling these two, is root of 2gh. So v prime is root 2gh. And we could say for the, so that's the speed of our bullet. Here we'll say 1 plus capital M divided by lowercase m root 2gh. This, of course, outweighs the 1 by quite a bit. It's the exact expression there. So, since energy is not conserved during the collision, we have to separate those two processes. And I'll just make up a couple of problems with this that we can, turn in next week and discuss next week. That'll be the last couple of easy ones, just to have something to potentially put on the exam. So this is a good one. So what we'll imagine is we'll have, I'll use 1 and 2. So we'll have M2, M1, and treat this with, and I'll put an L here. And I'll put an initial angle theta. So we're gonna release from rest, release M1 from rest. And M2 is at rest, and they're gonna collide and swing up a certain amount, okay? So they're going to collide, stick together, and swing up. So we release from rest, and we have perfectly inelastic collision. Elastic, and then, right, of course, there's gravity. And then what's gonna happen is they're gonna come up to some height, and they will be welded together now, okay? So they're 1 and 2. And you know, it's probably just as well to just ask for the height. Asking for the final angle is just a, asking for the final angle is just an extra piece of trig, doesn't really add any physics. So we could even call this H here, and we could call this H prime, and we'll say solve for H prime. Perfectly inelastic, pretty fine H prime. Because we're doing it in terms of these two general masses, we'll have a bunch of limiting cases, right? You can always check your answer with the limiting case. For example, what if M2 is much, much smaller than M1? How high is it going to swing? M2 is really light, M1 is heavy.
M2's gonna go much higher.
Well, remember, they're going to stick together.
Oh.
They're both sticking together, yeah. If they were,
Okay. I don't think it's gonna go that often.
this one's light, this one's heavy.
Oh, that was.
Yeah.
It's gonna go just above.
Actually, if this one's really heavy, this one's almost not there, then it swings to the original height, just by
Yeah.
conservation of energy. Right? If this one's much heavier than the projectile, then it'll just be stuck at the bottom. Point is, you have a full range of possibilities. So this H, depending on the ratio of these masses, can be anywhere from the original one down to nothing,
Oh.
right, in the limiting cases. Like if this one were really a bowling ball and this one were a ping pong ball with a little piece of gum stuck on it, right? Ping pong ball swings down, hits a bowling ball, sticks to it, and that's the end of the story, right? Now, this is for inelastic, okay, very important. If we had elastic collisions, then we'd have the other scenario. So elastic collisions, if M1 and M2 were equal, then this one would swing down, stop dead in its tracks, and this one would swing up to the same height, because that was the example of this one coming in and stopping, going up. So even a simple example like this has all kinds of good limiting cases for you guys to analyze. Of course, we never use numbers, and that's the reason in a class like this, so we can see everything that's going on. Good, so that is perfectly inelastic collision scenario. And my treatment here has all the essentials, right? We're essentially doing the same thing here, except now we have, it's gonna have a certain speed when it hits and so forth. But we know the speed it has when it strikes because of how high it fell. So that, uses all this stuff. Good, so that homework problem should be okay. And I'm gonna set up the elastic collision. I think we can get through all of the algebra on it. So our next elastic. We'll do one more inelastic collision. This one's important. Inelastic in 2 dimensions. So now we have an X and Y axis. suppose M1 is coming in along the x-axis, and M2 is headed here. We have a top view of this collision, and they're gonna collide here inelastically. So we're still doing a perfectly inelastic collision, like an automobile accident at an intersection where they stick together. So where does the wreckage end up? They collide and stick together. Where does the wreckage end up? I think we'd all agree it's gonna end up somewhere here in this quadrant, the first quadrant. But this is a pure vector problem. This could actually also be a football player running up the sidelines, and this guy's coming in is gonna make a flying tackle. Usually they don't do it at 45 degrees, but it's not impossible, right? We could actually come in at any angle. So what we have here is the vector version M1 plus M2 B prime. We just have the vector version of this equation, perfectly inelastic, so they stick together, they have a common speed when they're done. And the nice thing about this, I'll just draw some vectors. So before the collision, we're going to have a momentum vector. And here we're going to, I'll make this one longer, okay? So M2 is the bigger of the two. Doesn't have to be bigger mass, right? The product of mass and velocity is bigger. This is M2 V2. So this is nothing more and nothing less than an addition of two vectors. So we'll do this in a different color. And what we know is we have to go over this bar and up this bar. So this one we would call M1 plus M2 B prime. And in fact, since I had these vectors, I was labeling them. You could just leave the vector off there. So M1, B1 is the magnitude directions given in the picture, right? So this actually defines a triangle, which I'll just repeat here. You've got a triangle with this momentum plus M2 B prime. So here you could be analyzing the wreckage of a automobile accident and trying to assign the responsibility. So who was going too fast, for example? And in that case, you might know the masses of these two cars, okay? And you might know the angle. So basically, the way to think of these problems is just set it up and draw it and then analyze this triangle. Now you've got a triangle so you can solve for two unknowns, okay? There are two unknowns you can solve for here. And you have a bunch of relations. So you could say we have M1 B1 squared plus M2 B2 squared, M1 plus M2 B prime quantity squared, right? It's a right triangle with Pythagorean theorem. If it's not a right triangle, we have the law of cosine or something. Okay. And what else do we have here? You could say, well, the tangent of that angle is equal to M2 B2 over M1 B1. Well, as many relations as you can come up with. You have to be given enough information to solve for the whole thing. So I'll just put this up as a homework problem too. I'll just write etc. Now here, in order to have something to solve for, we got to make up some relations here. So let's say let M2 equal 2 times M1. just a demo, I'll repeat for us though. So anyway, what will we find now? Find V prime. That should be okay. Main thing is that this perfectly inelastic collision in 2 dimensions is a triangle. We're just going to analyze it. So that's good to know. So now I'm going to go back. I'm going to move into the elastic collisions that I was about to do. This is good. And I'll demonstrate it again. So the prototypical elastic collision is when an equal mass comes against the other equal mass. This one is moving, this one's at rest. This out here, and once again what we see comes to a dead stop. We reverse that, comes to a dead stop. Okay. If we strike the larger mass, this one moves a bit, but this one also bounces back. And if the much larger mass strikes the smaller mass, this is the interesting one. This one jumps out with extra speed. So our calculations are supposed to show that. And of course, actually, if I reverse this one bounces back, this one moves out with full speed. So the symmetric case is the one we're going to check for first after we do our calculations. The claim is that this set of phenomena is accounted for by conservation of momentum and energy. So I'm going to set those up to see how far we get. Good. So this will all be elastic. Picture is that what we just had on the track there. M1, M2, and they're going to collide, and they both can be moving. We're not just starting with one at rest, but we're starting with the full equation. So the linear momentum conservation would tell us that M1, V1, plus M2, V2. So that sum is equal to the same sum after the collision, V2 prime. And for energy, we would have the kinetic energies before and after. I'm going to cancel the 1/2 right away, right? We have a 1/2 in front of each. So we have M1, V1 squared, M1 V1 prime squared, M2 V2 prime squared. So if you just try to, you have 2 equations and 2 unknowns. So you can say I'll be given the V1 and V2 and I want to find V1 prime and V2 prime. But if you just try to go in with your quadratic formula, there's going to be trouble. So what we do with the second equation is take the M1, and we have the V1 squared minus V1 prime squared on the right side. And then on the left side, on the right side, we have the M2 V2 prime squared minus V2 squared. And by doing this, we can factor this because we recognize the difference of squares. So V1 minus V1 prime, V1 plus V1 prime, M2 V2 prime minus V2, V2 prime plus V2. And this new equation 2, we still have 2 equations and 2 unknowns. But here we can make a substitution. Well, we'll do same thing here, so here we have M1, B1 minus B1 prime equals M2, B2 prime minus B2. And now we see we can make a substitution. We'll take the M1 V1 minus V1 prime, take the right side here and substitute it down there. Okay. So with, this is the new equation 1. We still have two equations and two unknowns. And taking this one into the bottom one, we have M2 V2 prime minus V2 times V1 plus V1 prime equals M2 V2 prime minus V2 prime plus V2. And this has delivered goods. Okay. So there's a common factor, and we're now left with V1 plus V1 prime equals V2 prime plus V2. So that, put a box around it, and we'll keep these two equations now. So the two equations with the box, we've got rid of the quadratic aspect, and we can solve these two equations with two unknowns. They're just linear. So these two are the ones we're going to solve. And this trick with the difference of squares shows up a number of places in mechanics that you're going to want to have in the back of your mind. Good. So, okay, I'm going to erase these here in order to have enough room. And let's see what substitution we make. So, we'll replace the V1. So we're going to have M1, and the V1 is V2 prime plus V2 minus V1 prime. Plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, let's see what we get here. So we have V1 prime hold on, is that the one I wanted to replace? Let's try this again. Let's go with the field. We want to isolate one of the primes. Okay, yeah. Take two. Okay, so we want to isolate one of the prime ones, so let's go ahead and write M1 V1 plus V2 equals M1 V1 prime plus M2, and then our V2 prime will be V1 plus V1 prime minus V2. That'll be better. So V2 prime, V1 plus V1 prime minus V2. And now what do we have? We have M1 V1 plus M2 V1. That would be M1 V1, and then we have M2 V2 plus M2 V2. That's one had a minus sign, didn't it? M2 V1. Equals M1 V1 prime plus M2 V1 prime. This will do the trick. So we'll have equals M1 plus M2 V1 prime. So we can now solve V1 prime equals M1 minus M2 V1, M1 plus M2 plus 2 M2 V2, M1 plus M2. And we'll check this result there in a moment. Pretty sure this one works. And we can either do the algebra again for the second one, or we can realize that we should be able to just extract it out of here by exchanging all of the ones and the twos. So we'll always have that denominator, M1 plus M2. We will have 2 M1 V1 plus M2 minus M1, M1 plus M2, V2. Good. And sometimes your Physics 4A book will have these formulas in there, you know, in the relevant section. You can look them up. But provided we did the arithmetic correctly, we can now test the consequences of these. And the way we have them now, by the way, this could also be a matrix multiplication, for those who are interested in that kind of thing. So what we have now is the initial V1 and V2 on the right, and this is the result. The result of the collision is the V1 prime and the V2 prime. So let's just, we're running out of time, let's just test out the most elementary of these. Looks like we have just the amount of time to test this and see if we got it right. So the test for this, M1 equals M2, V2 equals 0. Because that's when we came in, the other one was at a dead stop, was stopped. And then we get V1 prime equals M1 minus M2, there's a 0, and there's a 0. So this is the one that came to a dead stop. Check. V2 prime, M1 equals M2, so there's a 0 there, and here we get 2M over M plus M, right? So that the maths are equal, that cancels the 2, and we just get V2 prime is equal to V1. So that was, and I'll just demonstrate it once more for the record. That was this one. We came in, energy was conserved, and this one was launched, and this one came to a stop. Okay. Successful theoretical mechanics calculation. Good, we'll leave it at that. I think the problem I put up there was the last homework problem. Right, we'll talk, you know, we'll have that in next week sometime. The other ones that we assigned are due today. And just wanted to get some, well, actually I put 2 up there, right? I had 2 up there. Those will be for next week. We'll just discuss them. I want to be able to throw something like that on the exam if necessary. Okay, good.